Another quick question.
I think we'll have to stop there because we're out of time. We can take the rest of the questions over coffee.
No, we can talk offline.
Okay.
Thank you. Let's thank the speaker again.
Thank you.
So the second talk in this session is titled Before and After, Managing Hierarchy, Partitioning, and Asymmetry for the Availability and Scale in Google's Software-Defined WAN. And the talk will be given by Chi-Yao Hong, who's an engineer at Google working on traffic engineering.
Okay, let's get started. My name is Chi. I'm from Google, and this is joint work with my colleagues at Google. And this is truly a cross-team collaborative project that the before network evolution will be impossible without a contribution from many, many others in Google network infrastructure team and network SREs. So in this talk, I'm gonna present our 5-year experience in evolving before Google's globally deployed software-defined WAN from a content copy network, which offers 99% of availability, to a highly available backbone network with 4 nines of availability, while at the same time supporting 100x more traffic. And this is a follow-up work based on our previous paper published originally in SIGCOMM 13. So just to give a little bit quick background on our first generation B4, that this is basically a simple design that it runs 2 layers of network traffic engineering controller. At the top layer, we have a logically centralized controller, which takes the side level topology and all pair demand matrix, again at side pair level as input, and calculate side level pathing via IP and API encapsulation. And the tunnels are programmed via a per site domain controller running within each site. So this central control of B4 traffic engineering pathing has proven to be invaluable. For example, it provides much higher efficiency compared with B2, which is Google's global backbone running RSVP on vendor gear. And because it's more efficient use of the network resource, we can significantly reduce the per byte cost. And also, the centralized controller offers more predictable behavior in terms of network convergence. And this platform also enables fast feature velocity. However, centralized design is also not a panacea. In fact, we have faced extreme challenges over the last couple of years across several dimensions. First, for availability, we have very stringent availability requirement. Initially, B4 had 2 nines of availability, which means that the packet loss must be below a certain threshold, and the promised bandwidth is available 99% of the time over a monthly measurement window. However, there are many applications in Google requires much higher availability, level of availability SLO, service level objective. And B4 was not allowed to serve these applications due to the lack of availability. Our initial target is 4 nines of availability, which seems daunting initially given that fiber cut and underlying infrastructure failures happens very frequently, especially for the long-haul gear, which will eat up our availability budgets. And also, the necessary management operations need to be done frequently over time, and that will also cost availability budgets. And one can stop touching the network to improve availability, but that's just wrong. We had to frequently upgrade our network for other requirements as well. For example, scaling. This is another grand challenge that we have faced in B4. Now we've seen that our bandwidth requirement has doubled pretty much every 9 months. And we've seen this trend quite consistently since the inception of B4. Looking at the traffic statistics, I've seen an incredible 100x increase in aggregate traffic demand over the last 5 years. We also had scaling challenges over multiple other dimensions, such as number of cluster prefixes and number of B4 sites, control domain, and number of tunnels. As we connect more and more clusters to B4, we have scaling challenges in all the dimensions. Along with availability requirement and scale requirement, we also want to make sure that any network upgrade does not disrupt the existing traffic that running through the B4 network. And also, we want the previous nice property to be preserved. To achieve those demanding requirements, we have to innovate aggressively by proactively designing, developing, and deploying new features and many point solutions to achieve our requirements. Okay, and in the rest of this talk, I'm gonna talk about 3 key lessons we learned from the evolution process, starting from the topology evolution. So this figure shows the first generation of the B4 site fabric we call Saturn, and it has 2 layers of chassis. At the bottom layer, we have 4 BF chassis that can be used to connect to the clusters, while at the top level, we have 2 to 4 CFs chassis that can talk to the WAN. So how do we scale this network? One option is that we can add 2 more CFs at the top level to make it 8 chassis in total, and that will give us more capacity towards the WAN side. However, this has its own limits, and over time we see this is way below our scaling requirements. So what we do as a conventional practice is to build multiple B4 sites in a close proximity, and then distribute clusters between those sites within the close proximity, which is called B4 campus. This was the convention options we followed. However, this practice was proven to be very bad, as over time, it caused multiple challenges that only manifest at scale. First, it significantly slowed down the centralized TE controller, which operated at the site-level topology abstraction. Second, we easily run out of the number of entries we can store in the switches, which impose a harsh table limit. Finally, and more importantly, this further complicated the capacity planning and job allocation process. App developer went from thinking about regional replication of their job within the same campus to have to understand that there's a potential network bottleneck can happen in the B4 backbone network. To solve this, we come up with a new topology called jump gate, which is a 2-layer hierarchy. At the bottom layer, we form a logical topology. Think about it as a logical router we call supernode. And this is built using a 2-layer cloud network using off-the-shelf merchant silicon switch chips. On top of that, we build jump gate site fabrics using supernodes as a building block. And we form a full mesh connectivity between the supernodes within the same site. And in the newer generation of a jump gate fabric, the site fabric can support up to 80 terabits per second, and this capacity can be flexibly allocated among WAN clusters and the site links, where the site links are the links interconnect the supernodes within the site. And we found this new topology has offered several nice benefits in terms of scaling and availability. First, it allows incremental update easily, right? You can, on demand, add new supernode to the site without worrying about the other sites. And also, it allows forklift upgrade of each supernode from one generation to the next generation in place without disrupting the traffic going through the other supernodes within the site. And finally, with the jump gate, we also further reduce the scope of our domain controller from the site to a supernode. And this reduction of the scope of a domain controller significantly improve our availability by reducing the blast radius of every misbehaving domain controller can only affect a small fraction of the Psi traffic. So we really want hierarchical topology for scale and availability reasons. But hierarchical topology doesn't really help unless we solve the topology asymmetry problem. Let me take this example to describe what asymmetry problem is. Suppose we have 3 sites here. Each site has 4 supernodes, and assume we have 4 bipartite connectivity is formed between supernodes across each pair of sites, right? And because our T allocate tunnels at Psi level, so we need to create the abstract topology at Psi level, right? And in this case, the Psi level link capacity is simply the sum of the supernode level link capacity. But this is only true when the network is symmetric. In this case, we can admit up to, say, 16 units of capacity and assume the traffics are balanced at the ingress side across supernodes. Then each router, each supernode can forward the traffic using ECMP, uniformly split across the next hubs toward the next site. And there will be no congestion happen. However, failures could easily happen. And if you think about that, if there's 2 links going down here, then can we model this again as sum up of all the capacity from the supernode level? The answer is no, because you will cause severe congestion where the bottleneck is the bottom router at the source site A. So in fact, you can only admit A units of capacity in your abstract topology to avoid congestion. And this is a big loss due to the topology abstraction, 43%. In fact, capacity asymmetry is unavoidable. Despite we plan our network to be perfectly symmetric, asymmetry can still happen due to inefficient striping, which caused 2% of the capacity loss at the median case. And in the tail case, we have 100% capacity loss for the 18% of the cases. That's due to the case where one supernode has completely lost its connectivity towards the next site. To solve this, our solution combines Psi links and supernode level TE. Coming back to this example, that we can form the Psi links that interconnect the supernode within the same site. Those Psi links are relatively inexpensive compared with the long-haul WAN links because they are local and short distance. In this case, if we apply the supernode level TE to low balance the traffic across supernodes within the site, in this case site A, then we can recover most of the capacity loss. However, adopting the multi-layer TE turns out to be quite challenging because we're already running our TE at the site level. Adding additional layer of TE at the supernode level is non-trivial. Look at this 2 kind of straw man proposal. On the left-hand side, we have a hierarchical tunneling that we already have tunnels run at the site level, and then we can recursively add additional layer of tunneling for the supernode level TE. And this is bad because our switch can only hash based on the 2 outer layers of the packet header. If both layers of a packet header are used for tunnel encapsulation, then the entropy will be too low and it will lead to the inefficient hashing. Or another approach we can consider is to run supernode level TE at all. Forget about site level. Collapse, we flatten the topology and just run the supernode level TE. And this will lead to exponential more passes in the network and eventually slow down our centralized controller runtime significantly, and it's not feasible. This option basically defeats the purpose of having a hierarchical topology. Our solution, called tunnel split group, is a supernode level traffic split and can run without packet encapsulation, and is calculated per site level link independently, so it's quite scalable in terms of computation. First, we model this as a flow problem, and we add each flow for each supernode in the source site. And we assume the traffic are well balanced across the ingress supernodes. And the problem here we're trying to solve is to maximize the admissible demand subject to the fairness and the link capacity constraints. So to do this, we adopt a heuristic co-exhaustive water field, which will iteratively allocate each flow on their direct path. For example, the direct path will be using the WAN link directly without using any side links at the source site. And we gradually kind of ramp up each flow with the same pace, while if there's any flow get bottlenecked, then it will next search for the indirect path, which will be, for example, in this case, let's say the blue flow experience a partial failure in the WAN connectivity. So it will start using the side links to load balance the traffic across through the other supernodes towards the destination. And the algorithm will continue to run until any flow cannot further find any path to have further allocation. We assign TSG splitting based on the amount of egressing traffic at each supernode. And we show that such allocation is provably loop-free. This heuristic is also quite scalable, as we can parallelize the TSG computation for each side-level links in parallel. Moreover, we find that this heuristic effectively reduces the capacity loss due to the topology abstraction. This is the same figure I showed earlier. With side links and TSG, the median loss is reduced from 2% to 0.6%, while the tail case where we had 100% loss can also be considerably mitigated. Without tunneling for the supernode level TE, updating TSG can also cause transient loops and black holes. The standard approach to solve this in the SDN consistent update, as Jen Rexford presented this morning, relies on packet tagging or versioning to enable the safe network updates from a current state kind of to a target state. However, adding extra layers of encapsulation causes the hashing problem, as I mentioned above, and it's not a feasible option for B4. Our solution shared the same idea with the prior work on IPG update by modeling the TSG update problem using the supernode dependency graph. By updating the supernodes based on the reverse topological ordering of the dependency graph, we can achieve loop-free forwarding loop-free update while using only one or two steps in majority of the cases without requiring the packet tagging. So hierarchical TE is great, but it also at the same time requires fine-grained this multi-layer traffic splits, and which can easily exceed our switch table limits. So the solution here is that we implement a hierarchical traffic engineering split across different switches by leveraging the fact that our class network, our supernode fabric is a cloud topology, which has a spine layer that traffic will be bounced before they leave in the fabric. So this mechanism allows us to run hierarchical TE at our target scale with 6% more throughput, which is quite substantial in absolute terms at our scale. For more details, please see our papers. To sum up, we start with a flat topology in B4, and we deploy our first generation software-defined networking traffic engineering tunneling stack in B4 in 2012, which allows us to run this dual stack where T as an overlay and then the shortest path as the backup. And with that, we are able to achieve 99% of availability and running 2 service classes. And then we introduced the jump gate fabric, which has a hierarchical topology to improve the scale and availability. And to solve the capacity asymmetry problem, we further introduced a TSG tunnel split group to achieve hierarchical DE to rebalance the traffic across supernodes to match the egress capacity asymmetry. More recently, we achieved 4 nines of availability by re-engineering our domain controller stack with a more efficient switch rule management and more service classes. And this is done concurrently with supporting 100x more traffic. And we evolved the B4 into a highly available massive scale network. To conclude, B4 with high availability and plentiful capacity can offer unique benefits to cloud services. For example, Google Spiner can fetch massive amount of data from the remote cluster to the local one on the serving path without requiring co-locating the storage and the compute in a close proximity. For future work, we would like to offer even higher availability SLO by reducing the blast radius of any network event to deal with, for example, rare zero-day bugs or failures or incidents. Okay. So this concludes my talk, and I'm happy to take questions.
Thank you.
Hi, Rob Sherwood, Facebook. Thanks very much. It's great to see the problems that people run into, and especially when they start to look familiar. Can you jump to slide 26? I guess I'll ask my question as it's coming. But so essentially, given this problem, did you happen to look at non-equal cost multipath? Because that, at least to me, seems like a more natural solution.
Right. So we did look at that. So basically, TSG solution, maybe I was not clear, it's also non-equal path allocation, right? Okay. And when I compare with the naive solution, which is without the side links, there's really nothing much to do in this case, right? For example, when I showed this kind of toy example, that the bottom router of the source side actually have 2 units of capacity going out. So that becomes an obvious bottleneck, right? Another approach is that you can kind of do the WCMP even before the traffic entering the B4 side. And this is adding more complexity to the network, and we leave it as a future work for now.
Okay, I guess the latter is what I was talking about. Cool. Since there's no one else, quick follow-up question.
Sure.
The other thing was, it seems like you had to jump through a couple of hurdles because you couldn't get hashes on both the inner and outer IP packet. Did you consider only doing hashing on the inner packet? Because presumably that's where all your entropy is. And I do believe the hardware is capable of that.
Yeah, so there's actually multiple workarounds for that. And really the thing we are trying to avoid is to have a simpler solution. So if we see it's possible to not having additional layers of in-cap, and that actually reduce our dependency on the switch requirements. For our switch constraints, there are things like if you do 2 layers, right? Even if we solve the hashing problem, there are cases like we cannot do double in-cap in the same switch, and there's certain limitation that will impose, and we want to, reduce the requirements over on the switch side.
Thank you very much.
Mm-hmm. Thank you.
Hi, this is Nagakata from Salesforce.com. This is a nice talk. It's kind of nice to know the inner goings on of large topologies like this. So one of the issues that we've seen in our global data center infrastructure is the problem of IP isolation. I don't know if this handles IPv6 or not, but unless you were brave enough to migrate all your workloads to IPv6, you still have to worry about a fixed pool of IPv4 blocks that need to be allocated across data centers and so on. So did you ever face the issue of, as you are scaling this out, these data centers having to worry about these fixed IPv4 blocks, and you still have to try to kind of find ways to isolate their namespaces somehow?
Right, that's a great question. In terms of isolation property, I'm not entirely sure what's the exact property you're looking at, but I can give a little bit background on the B4 side to support both B4 and B6. So on day 1, we're adding new cluster, which is kind of B6 only, right? And then the trick we kind of do is to forward the traffic without requiring B4 to support B6. Through another layer of encapsulation, encapsulate to the B4 packet at the ingress side, and then decapsulate at the egress side. And then over time, we becomes fully compatible with both support V4 and V6. And in that case, we will necessarily will have more cluster prefix to match, and that does increase several scaling challenges in terms of number of rules we need to put as switches, and also number of kind of flows that we need to manage at a centralized controller.
Thank you.
One last quick question.
Basically, the question is the following.
You
talked about two challenges. One of them is basically convergence time, and the other one is scalability. Regarding convergence time, since you know all demands a priori, why you actually cannot work on basically configuration during, so we are talking about tense minutes, right? So basically, why you cannot use this time frame actually to install a configuration for the next cycle? And actually, since time synchronization is not an issue, actually you can later just using some coloring basically to switch between one configuration, between old and new configuration. In this case, convergence becomes not an issue. Also regarding scalability, so what is the scalability numbers is the second question. Since potentially you can decouple location from name and also basically create sufficiently enough number of passes and exploit them in your optimization process. In this case, you will be just independent from a number of flows it's running. So basically, if you can answer these two questions. Thank you.
I don't think I fully understand the first one. Maybe we can take it offline. For the second one, the key scaling challenges on the supernode level T is basically your exponentially more number of nodes, right? And the number of paths will grow exponentially to the number of graph. And there's potentially more better solutions that we can find to effectively solve it. And by naively applying our existing side-level algorithm to the supernode level, we simply find it does not scale well. And our switch cannot handle so many rules.
All right, thank you. Let's thank Chi again. So since we're talking about load balancing, there's lots of seats in the front if people want to sit down. It's rather congested in the back, but there's lots of room up here. So the next talk is titled on low latency capable topologies and their impact on the design of intra-domain routing. The talk will be given by Nick Gavazdiev from UCL. Nick is a final year student, but he tells me he's already accepted a job, so you'll have to make him a really good offer if you want to hire him.
Okay, so today I will talk about low latency routing, and I'll talk about low latency routing in the ISP setting. I will focus on how the topology and the routing each limit how well you can achieve low latency in this setting, and then I will demonstrate how today's state-of-the-art routing system often fails to provide low latency on exactly the topologies that have the greatest potential for low latency. Okay, so we all know that we want low latency. There has been some excellent work on providing low latency routing in the data center, and there has been some excellent work in providing low latency routing in the enterprise, such as B4, BWE, and so on. Now, in the enterprise scenario, the operator controls both the wide area network and the sources. So demands are mostly predictable. Now, this talk is not about that. This talk is about the ISP setting. And then in the ISP setting, the operator does not control the sources. So as you will see, this lack of control over resources is one thing that makes the ISP setting very challenging. And we'll talk about that more later on. Okay, so how are we going to get low latency in a moderately loaded ISP network? Well, what we can do is we can start with the topology. Now, obviously, the topology must offer diverse low latency paths. Or we can look at the routing. And obviously, the routing system must be able to make use of such good paths. Now, clearly, there is a dependency here between the two. And to the best of our knowledge, that dependency hasn't really been explicitly explored so far. Okay, so let's take a closer look. So here we have the set of all possible topologies connecting a set of pops. What I mean is, if you have a set of pops and you figure out all possible ways to connect them, they're there in that Venn diagram. And then what we're going to do is we're going to look at the simplest possible routing algorithm. We're going to look at shortest path routing. So in the shaded area here, you have the topologies out of all topologies where shortest path routing gives the lowest possible latency among all routing algorithms. Now, what do those topologies look like? Well, it's simple. They look like trees. So here we have a very simple example where the link capacities are each 1.5 units. And we have two aggregates, where an aggregate is just a bunch of flows that flow from a source to a destination. And those two aggregates carry 1 unit of demand each. Okay, so what will shortest path routing do? Well, it will route everything on the shortest path, as you can see here. Notice that you can't really achieve any lower latency on a tree-like network. Okay, however, we don't really like trees. We don't like trees because they don't provide any resilience against things like link failures. So if we want to have redundancy, we need to change the topology. So we're going to change the topology and improve it and then add a link. So notice, however, that the addition of this link changes the behavior of the routing because the shortest path now basically goes to the top for the bottom aggregate, which means that the capacity of the link is 1.5, and we have two demands of 1 unit each, so we have congestion. So great, what is the big deal about congestion? Why do we want to avoid congestion? Well, congestion causes queuing, and queuing inflates latency, and we want to minimize latency, so that's not gonna work. But it's not just that. Queuing is also going to, congestion is also going to eventually make those aggregates fit because congestion control will kick in, but that will hurt everyone's throughput. So we really don't want to have congestion within our network. Okay, so what we've done here is we have created a better topology. The topology is more resilient, but our routing system is essentially crippling our ability to provide low latency, the topology's ability to provide low latency. So we clearly need a better routing system. Well, luckily for us, we have modern traffic engineering, such as B4 and MPLS-TE. Now, those schemes, they will basically let us get the lowest possible latency on a much larger set of topologies. So how will they do in our example? Well, here is the same example with the new link added. It's very simple. They're basically going to route as much as possible on the shortest path, and then whatever does not go on the shortest path will go on longer paths. Traffic will be split. In this case, the bottom aggregate gets split 2 ways, and then the half of it goes on the bottom longer path. And notice that this solution does not have congestion, and at the same time, it still loads the top latency path fully, which means that it's also latency optimal. Okay, so what about this other region then? Do we have any topologies for which modern traffic engineering does not give the lowest possible latency? And perhaps even more importantly, do we care? If so, do any of those topologies have the potential to provide low latency? And why is it, if so, that current routing does poorly on those topologies? Well, I'm going to provide a proof by example that such topologies exist, and basically such real-world topologies exist. So here is the topology of GTS, the Central European Network part of it, and this is from 2010. We have looked at over 100 different topologies spanning a decade. It just happens that this example is from 2010. Okay, so what we're going to do now is we're going to do 100 runs of shortest path routing using synthetic traffic matrices. And we're going to generate the synthetic traffic matrices using the gravity model that the community uses when generating traffic matrices in the ISP setting. And then I'm going to plot a CDF of those traffic matrices. And then on the x-axis, I'm going to plot for each traffic matrix the fraction of flows that cross at least one congested link. Okay, so here's what the results look like for shortest path routing. And notice that each point is run on a different traffic matrix. Now, notice that shortest path routing does extremely poorly, just as expected. About half of the time, half of the aggregates experience some sort of congestion. Okay, so let's try a more modern routing system. Let's try B4. So when I talk about before in this talk, I will talk about before the routing system, not before the topology that you just heard about. This is before as it was presented in 2013 in this paper. Now we can see that before definitely does better. However, there still is congestion. So why? Well, let's zoom in a little. So this is what the topology looks like. And then we are going to focus on this small part of the network. Now, keep in mind that what B4 does is essentially it routes greedily. It basically allocates as much as possible on the shortest path and then spills on to longer paths. So that's exactly what we're going to do. We're going to focus on flows between those two cities here in Hungary. And then there's going to be some other flows which just cross that part of the network. And we're going to allocate everything on its shortest path, which is indicated here. Now notice that the first link on the green aggregate's shortest path is now full eastbound. And now what the algorithm says we should do is we should allocate the longer paths. So what is the second best path for that aggregate, for the green one? Well, this is the second best path, but note that the second best path is already full. Using that path will result in congestion. And notice that there really isn't any other path that we could have used because of the greedy nature of greedy routing, we have essentially locked ourselves out of capacity. Okay, so let's take a step back. So why did this happen? Well, we observed that rings embedded in a topology can trigger this problem with greedy routing. Okay, so we know that before doesn't work that well. Shortest path routing doesn't work really at all. So the question is, does there exist a placement that actually works? Well, yes. There exists a placement which both avoids congestion and minimizes propagation delay on all of our topologies, traffic matrices, in this case. So then GTS is clearly sort of amenable to low latency, looking at that graph, at least for the traffic matrices that we've tested it with. So what about other topologies? We come up with a way that does not require a traffic matrix that will let us see if a topology is amenable to low latency. So it looks like what we need is a metric. And we need a metric that should be traffic matrix agnostic and should be routing algorithm agnostic. We want to capture two things. We want to capture the topology's potential to basically route around congestion hotspots. And we want to be able to do so without incurring long propagation delay, because long propagation delay is against latency, is against low latency. Okay, so essentially what we want is a metric that rewards alternate paths with short propagation delay. Okay, so let's see how we're going to get a metric like that. Well, here we have a very simple network, and we're going to only focus on 2 POPs. And we're going to try to fit y gigabits per second of traffic between those 2 POPs. Why y gigabits per second? Because this is the capacity of the shortest path between those. And then keep in mind that the shortest path in this case has t milliseconds of propagation delay. Okay, we're going to do something very simple. We're going to look at each link on the shortest path in turn, and then we're going to exclude it from the network. And then we're going to ask the simple question, can we route y gigabits per second over one or more alternative paths that have a delay less than 1.4 times the delay of the shortest path? So 1.4 here is a threshold for sort of good enough propagation delay. Okay, so let's try it with the first link. First link is fine. This is what the alternative looks like. And as we do this, we're going to keep track of the number of links with viable alternative paths. And this is 1 because we've only tried the first link. So let's try the second link. Second link is fine. Third link is fine. The fourth one, however, its only alternative is a path which is either too long or it doesn't have enough capacity. So we're not going to increment our counter for that. The fifth link is fine. And then we end up with 0.8. So this means that for this POP pair, 80% of links on the shortest path have an alternate path with acceptable low latency. And we call this the alternate path availability for this pair of POPs. Okay, so we have this for a single pair of POPs. How can we condense this to a single metric for the entire topology? Well, we need to compute this for all POP pairs. And then what we can do is we can basically compute the fraction of POP pairs that have good path availability. And this will be our metric. And what we mean by that is the number of POP pairs with APA more than 0.7 divided by the total number of POP pairs. So 0.7 here is empirically derived, and the metric itself is not very sensitive to picking different values. Okay, so great. We have a metric now. So we have this low latency path diversity metric. So what were we going to do with it? Well, we're going to take more than 100 real-world ISP topologies, and we're going to rank them. To the left here, you will have the ones that have low path diversity, and to the right, you will have the ones that have high path diversity. This is on the x-axis. So on the y-axis, we're going to generate a number of traffic matrices for each topology, and then we're going to plot the fraction of source-destination pop pairs that cross at least one congested link. So the fraction of pop pairs that are congested in this case. So, okay. This is what the results look like for shortest path routing. So for each topology, we're going to plot 2 points, the median traffic matrix and another point for the 90th percentile traffic matrix. And then the line between the two will basically show the spread of the distribution. Okay, clearly, shortest path routing doesn't work so well. Basically, networks with high LOPD, they offer a lot of alternative paths, and then shortest path routing experiences congestion. So that's not a surprise. So what about B4? Well, B4 does significantly better. If you compare this graph with this one, B4 does much, much better. It's much better at using alternative paths. However, there's something else we should be looking at. So the top part of the graph only tells us about congestion. The other thing is propagation delay. We can look at the total propagation delay of all flows divided by the total propagation delay if all flows are routed on the shortest path. This will give us what the latency stretch is for each of our traffic matrices. And then what happens is we have this graph where to the top you have congestion, basically delay due to congestion, and to the bottom you have delay due to propagation delay. And then we want them to sort of meet in the middle. We want a good performance is if everything is as close to 1 or 0 as possible. Okay, going back to sort of our example with B4, notice that in the bottom part of the graph, some flows are routed on non-shortest paths, and that is fine, that is expected, because once things do not fit on the shortest path, you need to go on non-shortest paths, so that is okay. What is not okay is that B4 still incurs congestion, and it does so on precisely the networks that have high LOPD. Those should have the highest potential for low latency. Okay, clearly we need a different routing scheme, so if we're so afraid of congestion, how about picking a routing scheme that just prioritizes avoiding congestion above everything else? How are we going to do that? Well, here we have a simple example where an aggregate fits on the shortest path. What we're going to do is we're going to just spread it out as much as possible. So we're going to spread traffic out to leave spare capacity in case traffic levels increase. And this is a well-known technique known as min-max. Now, notice that this technique does not really care about propagation delay. So how does that do? Well, it does really well in avoiding congestion because it was designed to do that. So it basically avoids congestion. However, note that it does route some flows on paths with very high propagation delay and with basically high latency stretch, which is expected. Okay, so min-max is basically one extreme of the design space. Is there a different extreme? Is there another way of providing a solution that avoids congestion, but then doing something else? Well, yeah, what we can do is we can minimize the propagation delay while avoiding congestion. And then this has the effect of maximizing the utilization of links on low delay paths. And this is what we call the latency optimal placement. Now, let's for now assume that it is possible to compute this at scale, and I'll tell you more about that later. Okay, so we have this latency optimal placement, and then that one is to the right, the one that minimizes propagation delay and avoids congestion. And to the left, we have min-max, the one that just minimizes utilization. So those are the two extremes of the congestion-free routing spectrum. Let's zoom in on GTS, which has been our running example. So notice that GTS sees a 5 times difference in propagation delay between those two extremes, which is massive. So let's focus on a single traffic matrix to understand why this is happening. Well, here what we've done is we've picked a traffic matrix out of the ones for GTS, and then we have plotted basically the CDF of the link utilization in the latency optimal case and in the min-max case. And you can see that even though you saw that there was a very significant delta in propagation delay, the mean utilization is pretty much the same of links, except for the top. Links on short propagation delay paths are in demand in latency optimal placements. So let's zoom in on that one. Keep in mind that all possible congestion-free routing solutions will lie in this range between min-max and the latency-optimal routing. Now, you may notice something interesting, and it's that some links are loaded up to 100%. Now, how feasible is that? Remember, this is not an enterprise network where we have sort of control over the sources. This is an ISP. That's clearly not very feasible. This is what traffic looks like on a core link. So what we can do is we can just use the mean rate. We can just route everything based on the mean rate. We could run traffic through a path with this much capacity, but that will cause us to have at least transient queuing delay. So instead what we need to do is we need to allocate headroom to allow for availability. Essentially, we need to allocate a little bit of slack. So we know that the latency optimal solution is not feasible because of variability, and we need to allocate headroom. And the question becomes, how much headroom should we allocate? Well, if we take this headroom dial and we turn it all the way up, and we allocate the maximum amount of headroom, we will end up with min-max. And then once we sort of start turning that dial the other way, we will start to converge towards the latency optimal solution. We're essentially exploring the state space. Now, keep in mind that we need to allow for the minimum amount of headroom in order to cope with variability in this case, because having a lot of headroom will hurt propagation delay. Okay, great. So we have this headroom dial, and then basically we have this latency optimal solution. So how are we going to get those two and combine them into a real routing system? Well, first we need to compute the latency optimal routing solution, the one without headroom. So we expressed the problem as one big linear program, and then we came up with an efficient sort of iterative solution that lets us compute this at scale. And then once we have computed that, we need to tune the headroom dial to drive the routing as close as possible to the optimal solution without avoiding congestion. And to do that, we can predict how aggregates will statistically multiplex on a path by convolving their path demands. There's more details about that in the paper. Okay, so the big question then is, at the beginning of this talk, I showed that a routing system may not be able to unlock the low latency potential of a topology. And also we had this metric of LLPD that indicates that the topology has good potential for low latency. So what if no one ever builds those topologies? Will anyone ever build a modern wide area network with high LLPD? Well, sure, you just saw one of those in the last talk. So we repeated the shortest path routing experiment, but then we added Google's B4 network. And it turns out that it has the highest LLPD of all networks in our data set. So this is a modern high LLPD network. Now, interestingly, B4, the routing algorithm, does great on B4, the network. So could it be because the routing algorithm and the topology somehow co-evolved? In general, what topologies would people build if they knew that the routing system would always extract the best from the topology? And I will leave you with this question. And I will take questions.
So we have time for questions.
Do we have questions?
Anya.
I'm sorry, I can't hear.
Can we have the mic on the side over here? Just 1 second.
Okay, you already mentioned one part where there is co-evolution, and that is the traffic, the routing and the topology go along.
Yes.
But of course, also the traffic matrix goes along with the topology that you have, because if you're noticing you're running into headroom too much utilization, you're going to add links accordingly. So to which extent is it reasonable to pick all of these random traffic matrices rather than a traffic matrix that actually fits the topology?
Well, we haven't picked them at random. So they are generated using a gravity-based model which takes into account the topology.
And of course, the next question is, a lot of time when you determine your routing, you actually care about the fact that a link may fail and that you have enough capacity to actually account for all of this. Did you increase that? And also, the other part is the traffic matrix isn't static. It changes all the time. And even though you might predict 100% utilization in reality because of fairness, et cetera, you're actually way below that.
Yes, of course. So if you look at our slides, our sort of utilizations, you can see that our traffic matrices are not really that. Where was that? Yeah, this is the link utilization in an example of the traffic matrices of the type that we use. You can see that the traffic matrix is not extremely loaded. So we did we did not, of course, load them up to saturation because that would be pointless. We did leave quite a lot of spare capacity. Yes. Yes. Yes, what?
Can you repeat your points?
Oh yeah. So the follow-up of the question was that because the traffic matrix is not static, what will happen is if some parts of the network are loaded, basically users will not use those parts of the network, and that changes the traffic matrix. That is correct, but that is correct if your system does not attempt to alleviate congestion from that part of the network. So yes, I agree, they are all dependent up to some extent, and that's why we tried to come up with a metric which does not depend on the traffic matrix.
Okay, one last question, Chi?
Yeah. Hey, great talk, Nick. Quick question about the min-max computation. Do we use the linear program to solve this problem, or some kind of linear program variant?
Yes. So we actually, it's not very straightforward. So what we did is, yes, we use a linear programming sort of a formulation, but then we also wanted to be completely fair. That's why when there is a tie, what happens is we break it towards low latency. So it is true that we just use the linear programming formulation, but it's a little bit, it's all in previous work. So
when you solve the min-max, if you use the path constraint linear program, would you be able to specify only the lower latency path that will allows you to more explicitly trade for latency with the utilization?
Yeah, that's a great question. So we did try that. We have results about that in the paper. We basically have results where for each aggregate, we only picked the 10 shortest paths. So we didn't give the optimizer all paths, and you can read about it in the paper.
Okay, let's thank Nick again.
Okay.
Okay, and now for something completely different. The last talk is asynchronous convergence of policy-rich distributed Bellman-Ford routing protocols, and the talk will be given by Matthew Daggett from Cambridge. Matthew's also a final year student. He's looking for a job with the geographic constraint that it be deep in the southern hemisphere. He'll be moving to Perth.
I will do it. Okay. Okay, thank you very much all for coming. This is work, thank you for Nate for reading out the very long and tortuous title. In retrospect, we might have named it something a little pithier. This is work done with Alex Gurney and Tim Griffin. And what the title really means is that we're trying to reason about, okay, bit of a lag. New correctness results for general policy-rich distance vector and path vector protocols. So I'll explain what we mean by policy-rich in a minute. But at a high-level overview, we've come up with a new proof technique which allows us to directly avoid reasoning about the asynchronous nature of the protocols. And now that we don't have to worry about the asynchronous nature, we've been able to prove much stronger and more general results than previous work. Furthermore, all of our results have been formalized in the theorem prover Agda, and the results can be extended with specific protocol implementations to test whether that implementation in particular is correct or not. So, when I say I study routing for my PhD, I tend to get two responses. The first from non-computer scientists is like, wow, that must be really hard, very gratifying. The response from a typical computer scientist, though, is, why are you doing that? Isn't that solved? Bellman-Ford algorithm, you know, shortest path, all good. Well, today we have a routing protocol that runs most of the internet, a path vector protocol, BGP, and if misconfigured, it suffers from some fairly serious problems. The first of these are routing oscillations, i.e. non-convergence. So you can have two final states. So for instance, in here, we're routing from, you can either route from C to B to A or from B to C to A. And the protocol will continue to switch between these two configurations indefinitely, forever. And this is obviously going to have serious effects on traffic flows and is going to result in poor end-user experience. We have other problems, such as multiple final states, aka non-deterministic convergence. So here we have the same two final configurations. This time they are stable, so if you reach one of them, you're going to stay in that configuration. However, the state that you're going to end in is non-deterministic, in the sense that if you have a different ordering of messages between the routers in the network, you're going to get to a different end state. This is problematic, for instance, if one of these is your backup route and one is your main route, and 98% of the time your network configuration is going to fall into your desired intent, which is routing your traffic along the primary route. However, if you get a very pathological sequence of messages, then 2% of the time you might end up funneling all your traffic down your backup route, which might be very expensive. So, when we talk about correctness, we mean we want to guarantee that there is convergence, always, and we want to guarantee that it's deterministic, so we're always going to reach a desired state. And therefore, if you end up in the wrong state, well, that's the fault of your specification of your policies rather than just the design of the protocol. So, in order to reason about these problems, we want to reason about all path vector protocols, or as many as possible, all distance vector protocols. So we're going to abstract the key features of a routing protocol into a routing algebra. The first component of routing algebra is a set of path weights. So think of shortest paths. In this case, it's just the natural numbers. 1, 2, 3, 4. It's all the possible distances you can have in your network. We then have a choice operator, plus, which is defined on weights, and this represents choosing between two different weights of paths. So if you have x plus y, well, then it's going to return the best path weight out of x and y. So in shortest paths, this is the min, because if you have two distances and you want two paths with two distances, you want to choose the path with the shortest distance. The third component is a set of policy functions, f, that are going to be used to label edges in the network. If you've ever configured a router, think of f as a route map, perhaps. Classical routing theory often models these edges as labeled with weights themselves, but the functions allow us to model conditional policy and more expressive things, just like route maps. There are also some weak axioms for plus and f that we assume. These are very natural. For example, x plus y is the same as y plus x. Choosing between two routes doesn't matter which you provide first. So, using these abstract primitives, we can now answer the question, why do computer scientists think that routing is so easy? Well, that's because in all the undergraduate lectures, in all the examples that are given in routing textbooks of best path problems, the algebra is what is called distributive. And this means that it obeys the following equation. which says that f of x plus y equals f of x plus f of y. And that's for all functions f and for all roots x and y. What does this mysterious equation mean? Well, imagine that you're at node A, and B is perhaps your service provider, and C is your destination. Well, it says that if you let B choose the route between x and y, and then you extend it, you get exactly the same result as if you get to choose between the two extended routes yourself. So what does this mean intuitively? It means that all nodes in the network share a common preference order over routes. Everyone agrees about how good each set of routes are. Unfortunately, in the real world, it's not so easy as this. Many routing problems are not, the algebra underlying them is not distributive, and in fact, BGP is one of these. Unfortunately, all the correctness results, all the classical correctness results of distributed Bellman-Ford, path vector, distance vector protocols rely on distributivity in the proof, which obviously leaves us a bit adrift. So, let's quickly show an example of toy algebra. We're not suggesting that this is, you can interpret it as you want, but just an example of how distributivity might be easily violated. So, we're going to look at shortest paths where you can't accept any paths with no more than one blue edge. So edges in the network are labeled blue or not blue, and you want the shortest path with the constraint that, you can't have a path with two or more blue edges. So in our example before, x, the top root, is going to be a blue edge, and y is not, x top root already has one blue edge in the path, and y has no blue edges. And the edge from A to B is blue. Unfortunately, your service provider much prefers the X route, the top route, which is great because it might be shorter, for instance. Unfortunately, the link from you to your service provider is a blue route. And therefore, although your provider is making the choice to go on X, you can't use that route because it now has two blue links. You'd really prefer to take the route f of y. This is, and you end up with no connectivity in this example. So we're going to define a policy-rich algebra as an algebra that violates this distributivity constraint. It's kind of, the algebra is non-trivial in the fact that other nodes disagree about preferences. So, thankfully, Sabrina came to the rescue in 2005 and showed that there is, in fact, a hierarchy of correctness conditions for path vector protocols. At the top, you have distributive algebras, which has been discussed in the long history of semi-ring routing. In the middle, you have strictly increasing algebras, and at the bottom, you have networks with only algebraically free cycles. Now, I'm going to describe what each of these means, but what we claim is that in many path vector routing protocols, what you're looking for is strictly increasing algebras. That's the Goldilocks condition. Not too strong, like distributive algebras, and not too weak, like networks with only algebraically free cycles. So let's quickly recap. Distributivity was this equation. Everyone has a common preference order. What are the advantages of this? Well, you get a global optimum out of your routing equation. This means that the routes that you're assigned, that a node is assigned to, is guaranteed to be the best possible route through the network. The disadvantage, as we've discussed, is that it's very restrictive as to the routing problems you can solve. On the other end of the spectrum, we have the cycle freeness condition. And a network's cycles are free with respect to an algebra if going round a cycle in the network is never an improvement. So in terms of shortest paths, what does this say? It says that there are no negative weight cycles in the network. What are the advantages of this condition? Well, it's the least restrictive possible condition in the sense that it is necessary for convergence. If your network is not algebraically cycle-free, then your protocol is guaranteed to diverge. However, it comes with some quite significant drawbacks. It's now a condition on the topology of the network and not just the algebra. This means, okay, great, you've managed to verify that your network is cycle-free. Unfortunately, someone adds a link to your network. You now have to go through the entire process of re-verifying that the network is cycle-free. Furthermore, in order to check cycle freeness, you're probably going to require global coordination. You need to know everyone's the policies that people are using, the Fs that people are using, which obviously if you have a network with many actors in, they may not want to divulge their policies. Furthermore, actually, in the general case, verifying whether a network is cycle-free, even once, is an NP hard problem. And therefore, actually, even doing one of these checks in the general case is computationally infeasible for any reasonable sized networks. While we're here, for those of you who know about the Gao-Rexford conditions for BGP, they can be interpreted by looking through the lens of cycle-freeness, and they prove that if ASs obey their customer peer provider hierarchy, then they show the moral equivalence of that the network is guaranteed to be cycle-free. Obviously, it comes with the same drawbacks as all of these. When you add links to the network, you have to check. You have to re-verify that you obey this hierarchy. And also, they require global coordination in order to guarantee that you actually do obey this hierarchy. So we then come to the Goldilocks condition, strict increasingness. And an algebra is strictly increasing if extending a root only makes it worse. So if you have a root x and you take f of x, well then f of x has got to be strictly worse than x. We define this ordering using the plus operator. So if x is less than y, if you choose between x and y, well, you choose x. And then x is strictly less than y is defined in the usual way. What are the advantages of this? So it's a property of the algebra. Hence, it's independent of the network topology. So we only have to verify it once when we design the protocol, and it will automatically work for all networks. It's much more expressive than distributive algebras. This means that you're not enforcing all nodes have a common preference order. All you're saying is that, OK, if you're extending a route, you've got to make it worse. We don't care how much worse. It's just got to be worse. Furthermore, it has the advantage that conditional policies, i.e. route maps, actually preserve this property. If you have two policies, both of which are strictly increasing, and you decide and you apply them conditionally, perhaps depending on a community value or a AS in the path, then the resulting conditional policy is still guaranteed to be strictly increasing. Obviously, it being a Goldilocks condition, there are some disadvantages. You have local optimums rather than global optimums, so you only get the best path given the choices of your neighbors rather than the best path through the network. And it's only a sufficient condition rather than a necessary condition. So there do exist algebras which aren't strictly increasing, which do converge for some networks. But given a non-strictly increasing algebra, you can always find a network for which it will diverge. So what have we proved? We've proved that if an algebra is strictly increasing, our new results are that path vector protocols are always converged to a unique solution. Before, Sabrina only proved that it converges. We proved that it converges deterministically. We extend our method to distance vector protocols. So we've shown under the same model that distance vector protocols with a finite set of weights also converge deterministically, and in particular even policy-rich ones. So there's nothing wrong. You could easily design a correct distance vector protocol with conditional policies, not a problem. And finally, all of the above results do not require in-order reliable delivery that many previous results did require. So BGP is based on TCP to provide these guarantees. We've shown that it's entirely possible to design a correct distance vector path vector routing protocol where you have none of these guarantees. Messages can be lost, they can be duplicated, they can be reordered, doesn't matter. And our proofs, we've managed to do this by using some new techniques. This is the structure of our proof. I'm not going to go into the gory details. If you're interested, you can read the paper. At a very high level, Urston and Dubois in 1990 showed that if you have an asynchronously contracting operator, then that operator is guaranteed to deterministically converge. And then Gurney says 2017, that's when we put the paper on archive. It was actually 5 or 6 years before this. Managed to prove that if you have a certain set of ultrametric conditions, ultrametric spaces, then you are guaranteed to be an asynchronously contracting operator. And we've shown in our paper that if you have a strictly increasing algebra, well, it's guaranteed to obey the ultrametric conditions. As I've said before, all results have been formalized in the theorem-proving language AGDA. This means that our proofs are machine-checked all the way through, down to most trivial lemmas, including all the previous work we've shown on the slide. The library is freely available online. and is easily extendable in the sense that we've done this for abstract pluses and sets of functions f. It's very easy to define your own implementations of these and check whether it is strictly increasing or not. If it is strictly increasing, then the theorem prover will spit out a proof that your protocol is guaranteed to be asynchronously safe. So another question we might ask is, okay, well, what do these algebraic results tell us about BGP? Well, obviously BGP has all these problems, so the algebra must have some problems itself. The multi-exit discriminator attribute means that the less than or equal to ordering that we defined previously is not transitive. So if you have a root x and you prefer a root x over a root y, and you prefer that root y over a root z, then it doesn't necessarily follow that you prefer x over z, which is really kind of mind-blowing in many contexts, and it makes the protocols almost impossible to reason about. This can be fixed by turning on certain flags in BGP, which is perhaps the solution. Local preferences, the second major problem is that local preferences are erased in BGP. When you extend a route across an AS boundary, you remove the local preference attribute because it reveals your own routing policies. And therefore, you can have a situation where f of x is preferred over x, which breaks the assumptions that our proofs rely on. BGP is legacy, is legacy code. It's out there. It may be almost impossible to fix in some sense and make the policies less expressive. But we hope that our results may be applicable to intra-domain BGP applications such as data centers, where you have complete control over the policies. You don't need to worry about giving away implementation details, and therefore you can ensure that your policies are strictly increasing. Beyond BGP, we hope that these results will be used to develop the next generation of path vector and distance vector protocols, if the need be, and these can be safe and correct by design. So we are theoreticians for the most part, and we like lots of abstract maths. Just as a sanity check to show that actually this work we can define a real protocol using this, and the model is expressive enough to handle real implementation details. We have defined a policy-rich shortest path algebra, which is heavily inspired by BGP, in the sense that routes are tagged with community values, and the policies can make decisions based on community values, based on the path that the route was generated along, local preference values. Unlike BGP, the local preference values are not erased, which allows us to make it strictly increasing. This protocol has been defined, the algebra has been defined in AGDA, and therefore our proofs have guaranteed that it is correct, in the sense that for any network, for any sequence of asynchronous events, the final protocol is guaranteed to converge to a state which is unique, which is the same state every single time. And this is a very expressive protocol. It can easily implement the no more than 2 blue links example we showed. So, what are the open questions? Well, it would be great if we could incorporate these safety checks for strictly increasing this into automatic policy generation tools for examples where you have control over networks, so for instance, data centers. One such tool is Propane. Secondly, is it possible to have hidden information? So is it possible to hide your policy implementation details in a strictly increasing and still have a strictly increasing algebra? We don't have any strong ideas about this. Perhaps there's an impossibility result out there. And finally, what is the rate of strictly increasing algebras? We've allowed ourselves more expressive policies, which means perhaps the rate of convergence has got worse over distributive algebras. We show that that is the case in an upcoming ICMP paper in September, but actually we show that it's not too much worse. Okay, thank you.
Can you? I'm Nick from UCL. So I have a couple of questions. The first one is, I may have missed it, but in your example, the no more than 2 blue links,
yep.
Is that strictly increasing? Because if I have a blue link, the addition of another link doesn't really make my path worse if that other link is not blue.
So it's still shortest paths. So even if it's still shortest paths, so you still have to assign a distance to it. And therefore, as long as your distances are non-negative, it will be strictly increasing.
And then my other question is, you have proved convergence.
Yep.
And in that, for example, the no more than 2 blue links example, is there something about optimality?
So as I mentioned in the strictly increasingness slide, we get, when you ditch distributivity, there is no common preference order over routes, paths, and therefore you're never ever going to get a global optimum because everyone disagrees about.
Yes, but you are going to converge to a local.
But you are going to converge to a local optimum.
Okay. That was my question.
Great question.
So I have one quick question. One of the big pieces of this work is the fact that the messages are not assumed to be delivered over reliable in-order links. Yeah. And that enables, more flexible implementations. But what if you are using TCP?
Yeah.
Is there anything you can say about the conditions you need to ensure convergence? Anything new from your proof?
So they still, obviously the model assumes that there can be packet loss, packet reordering, so the proofs still work absolutely fine for in-order reliable delivery. As to whether you can strengthen the conditions, weaken the conditions needed in that case. It seems unlikely. The factorization of the asynchronous proof, the asynchronous part of the proof out, seems to suggest that actually the actual asynchronous details aren't the crucial part that require, aren't crucial to the proof that the protocol is somehow converging towards an optimal solution.
Quick question regarding the communities.
Yep.
Can you just add communities or can you also delete them and modify them?
Oh. So we have our policy language here. You can reject, you can add communities, you can delete communities, that's fine. You can compose them, so you can do multiple things with them at a time. You can have conditional policies, and you can increase local preference by, which is what ensures strict increasing.
That would suggest that you cannot use communities to implement something such as MEDs or local prefs, but wouldn't that be possible? I'm just a little bit puzzled. Because you could take your MED, add it as a community, and then implement a policy according to that.
I have to confess, I'm not quite sure. I'd be happy to discuss it offline.
Again, I'm just wondering about it, so I actually believe your proofs are really good, and it's a great step forward.
So the wonderful thing about it is that the proofs are checked by machine. So the machine, if the proofs don't hold, then it's computers that have, it's the computer is backing us all the way.
All right. So on that optimistic note, let's thank Matthew again. Now we're off to a break.